Okay. Now types of error. Just take down this one. Single bit error, multiple bit error, burst error. Okay. So first we will see about this error. Single bit error. From the name itself, we can easily understand that single bit now only one bit get error. Okay, so you see, this is my sender part. It's clear, ma? And this is my receiver part. Okay. So here, single bit error means what? This particularly, this bit have been changed here. So that is single bit error. But what is very big disadvantage now? It is detect only on a single bit. Okay, so that's why, because you've seen that my sender is sending the bit, and only thing is it is showing that the 0 is changed to 1 or 1 is changed to 0. That is called as a single bit error. Okay, multiple bit, actually it is reverse. More than one bit. More than one bit is there, that is called as a multiple bit error. So we have three types of error: single bit error, multiple bit error, burst error. Okay, so single bit, we all know that it is likely that it will detect only the single bit. Single bit means 0 is changed to 1 or 1 is changed to 0. That is single bit error. Multiple bit now, more than one bit. More than one bit consecutively 1 to 0 or 0 to 1. Okay, that is multiple bit error. Okay. Burst error. What is the mean by burst error? What is mean by burst error now? It having more than 2 or more bits have been changed. That is called as a burst error. You just see how many bits here now? 8 bits are there. Okay, 8 bits are there. In this 8 bits, we are going to see how the data have been. You see, here my 0 is changed to 1. And here my 0 is changed to 1. And here my 0 is changed to 1. And here also 0. So all these are corrupted bits. So burst error means just like not a single bit error, it will check for group of bits. So the group of bits it is checking. For example, it will take some 8 bit and it will check the error and find out the error. That is called as a burst error. It's clear. So if you are sending the data at 1 kbps now, the noise will be 11100. Okay, can affect 10 bits. And similarly, 1 Mbps now 10 into 10 power 3. So 10,000 bits it will affect. So the way they are saying it's single bit error will detect single bit, multiple bit error more than one bit, burst bit group of bits. Unit, they tell the word technically unit. Yeah. You all know that multiple bit error and a burst error, what is the difference now? When I'm going for, actually, when you see some of the books, they will take only single bit and burst error only. Some of the books, they will mention the word multiple bit. Okay, so the multiple bit means they were saying that more than one bit, and they didn't have the concept of like group of bit or checking or not. Okay, it will check more than one bit. But here, when I go for burst error, actually it is closely related only. It will take every 88 bit and it will check that they will check at a unit. So every unit will be taken and it will be checked. Actually, we will classify single and burst error. Burst error, we used to say that as a multiple bit error. But what is the difference now? It is only one bit. It is checking more than one bit, and it is checking more than 2 or more bits. That is the difference. That is the difference between the single bit error, multiple bit error, and burst error. Yes, have you identified the 3 errors? Have you all know that? Because I told you it's very important. This will check for 1 bit, more than 1 bit, more than 2 bit. Okay, it will check only. 1 bit, more than 1 bit, this is more than 2 bits. Yes, Sagar, have you understood? but normally single bit error have a limitation, and burst error is only thing. These two are grouped into as a only we tell as a burst error. Yes. Okay. Now listen, ma. It's why I told you redundancy. The word redundancy. What is redundancy now? That is extra bit will be added. That is called as a redundant bit. Okay, so there are so many methods of that. Okay, for example, I can add a group of redundancy bit, or I may add as a sum. Okay, so we used to say redundancy bit, redundancy sum, redundancy check. All these are related to redundancy. Redundancy means extra bit will be added. So when you see this, this is my data. Okay, this is my data now. This will be redundancy. This will be redundancy. Redundancy will be always appended with the original message. Always appended with the original message. Okay, so I told you we have a sender side and receiver side. So this is my message. Are you correct? Generator, you know, this is one algorithm, and in the generator algorithm, we have so many methods are there. That's why I told you it's one of the very important topic. So what we will do, how to create that redundancy method. So we have a LRC method, that is cycle redundancy check is there. Okay, and vertical redundancy check is there. So using some algorithm, we will generate the redundancy bit. That redundancy bit is appended with the original message. Okay, original message, and it is transmitted into unreliable. What is, ma'am, we are transmitting? You all know unreliable transmission. Why we are mentioning the word unreliable now? Because we are transmission in open medium. There the noise may be superimposed. So there is a chances of the bit is getting corrupted. That's why we are saying it's an unreliable medium. So now the receiver will receive along with the redundancy bit and the original message. We have an algorithm. What is the generator algorithms here? Here we have a checker algorithm. The checker will check, okay, with using which method they will check, and they will check whether it is correct now, it will keep that message, or else it will discard the message. This is the algorithm universally we are following in the error detection and error checking algorithm. Is clear? So you all understand that encode sender side, it's not a just we have so many algorithm. I told you redundancy, cycle redundancy check, vertical redundancy check. That's we will just add the redundancy bit and we will send. That is sender side get over. But receiver side will take the responsibility whether we can have to checking in that whether we received the original message or not. So the particular original message is not correct, it will automatically discard, and sometimes it will correct the error also. So we have a two thing, correct or discard, depending upon the algorithm. So you all know generator is one algorithm and checker is another algorithm, where we are going to see what are the error detection methods of that. Yes, you have any doubt on that? We all understand today. You people kindly take down the thing. Redundancy. Redundancy is nothing but extra bit appended to the data. It is nothing but it is sent along with the original data. Whether my receiver has to understand that my original message is correct or not. So for that, we are adding the redundancy bit. Have you understand this? Have you all take down redundancy bit, ma? I won't tell the meaning every day. It is nothing but extra bit will be added to the data. Yes? Clear? Clear, ma? Students, kindly acknowledge me. Yeah. Thank you. So, Soumya, I think full name I can't. Another. Soumya Deepdas. Okay. Am I correct? Pronouncing your name correctly. Okay. Yeah, Soumya Deep. Okay, and I already asked you on that day, ma'am, what protocol? Modulo 2 arithmetic. I told you we are using XOR concept. We all know what is XOR truth table. If both the bits are same, the result is 0. If both the bits are different, the result is 1. So while I'm performing my XOR operation, you all know this is here 0, 0, 0, 1, 0, 1, 1, 1, 0, 0, 1, 1, and 1, 1, 0. So when you see wherever I am getting 0, it is similar to that. Here the bit are getting different. Have you seen? Here the bits are getting different. So the modulo arithmetic, while I am performing, actually it's very, very important. Why you have studied earlierly this digital paper, now you have to understand. So modulo arithmetic, very simple. Remember 0, 0, 0, 1, 1 also 0, 1, 0 is 1, and 0, 1 is 1. Okay, and we all know that how we will perform now. A dash by B plus A B dash. This is the XOR formula. Through that we were computing and we are finding the XOR. And you all know this all binary addition. 0 plus 0, 0. 0 plus 1, 1. 1 plus 0, 1. And 1 plus 1, again we say 0, and the carry will be 1. Okay, and these are all subtraction process. So what you have understand from this modulo 2 arithmetic now, when you see here in that modulo 2 arithmetic, here see, when both the bits are same, when I performed binary addition or binary subtraction, the result will be 0. If both the bit are different, okay, whether it is a binary addition or binary subtraction, the resultant value is 1. So to that they are performing this modulo arithmetic. Okay, and you all studied the Hamming window. Did you remember Hamming window? We have the technical word Hamming distance. Okay, I think we just stop here. We will see directly the error detection. So what do you understand? XOR will be closely related with the binary addition and subtraction. If both the bits are same, the result is 0. If both the bits are different, the resultant is 1. Okay. Yes. Okay. Now I think I will go to the directly error detection method. Okay, that this is nothing but error correction. So we will see along with the Hamming. Okay. First, we will see error detection. I told you error detection is one of the very simpler way, whether we have a able to detect the error or not. So for that we are using the redundancy concept and we are finding the error. Okay, so redundancy means what? Extra bit will be appended with the original data. Okay, you please kindly take down this method, ma. Please kindly take down the error detection methods. It's one of the important part of question. Kindly explain error detection methods in detail. VRC, LRC, CRC, checksum. Okay, VRC, vertical redundancy check. Okay, vertical redundancy check. LRC, longitudinal redundancy check. CRC, cycle redundancy check, and checksum method. Please kindly take down. It's one of the important vertical redundancy check, longitudinal redundancy check, cycle redundancy check, checksum. Have you all take down? Have you all take down this mark? Kindly acknowledge it. I will go for the next slide. Yeah, vertical redundancy, longitudinal redundancy, cycle redundancy check, and checksum. It's one of the important part B method error detection methods. Have you completed this? Okay. Yeah. Shall I move on to the next slide, ma? Yeah. Kindly tell me, ma. Shall I move on to the next slide?
And again, we use the two formats to get the two matrices.
Yes, yes, ma'am. Okay. I think you participants cannot able to unmute. Okay. I think I will allow you to unmute and talk. That's it. Because normally I will get it. Okay. Actually, we are getting some of the students are not allowing this kind of thing, but I think you people are will behave genuinely, and then only the interaction will be more. Now you can able to unmute and talk me, and you may clarify the error because I told you it's the most important check. Okay. Parity check. Okay. So the parity check, we have a two-dimensional check method, simple check method. method and all. Okay. Actually, we will use to say the vertical redundancy check. It's nothing but a simple parity check. Okay. Simple parity check method is called as a vertical redundancy check method. Okay. So this simple parity check can detect only all single bit error. Okay. The problem is it is not possible on detecting the burst error. Why? Because we can say now there will be a number depends upon number of ones and zeros only we were doing this performance. Okay, but simple parity check or vertical redundancy check, this is the first method. I think, can anyone tell, actually in this parity check we are going to perform even parity method. We are going to perform even parity method. What is even parity method means? You all know that if even number of 1 is there, what I have to add? If even number of 1 is there, na, what is my parity bit, ma? Tell me, can anyone tell? Even number of 1 is there, na? In my data, even number of 1 is there. Okay, so what is my parity bit? What is my parity bit? Hey, kindly tell me, what is my parity bit? 1 0 1 1 1. Here how many even number? 4 ones are there. So if I even parity means I have to add 0. I have to add my parity bit as a 0. Okay, if odd number of ones is there, odd number of ones is there. For example, take the data 1 0 1 1 0. Here only 3 ones are there. So I have to add my parity bit as a 1. So you all understand, this is the simple way of adding the simple parity check or vertical redundancy check. It will perform the even number of ones and odd number of ones. Okay. Now you just see, students, are you there? Are you listening? Yeah. Yes, thank you, Soumya Deep. I think you may, Soumya, you may unmute and you may talk to me if you have any doubt. Okay, so you just see, this is the diagram. Okay, sender and receiver is there. You all know this is my data word. Okay, it having 4 bits. And I told you generator is nothing but adding the parity. There are so many algorithms. We have seen that vertical redundancy check, longitudinal redundancy check, cycle redundancy check. So it will follow one generator. And here I told you the parity bit is added. Very simple. Even number of ones or is there. Even number of 1 is there. Then automatically my parity bit is 0. Odd number of 1 is there, my parity bit is 1, because my data always consisting of even number of ones. That is the odd thing. If even number of 1 is not there, then automatically my receiver will discard the data. So here the code word, we all know data word, code word. We are using 2 things. Data word is nothing but an original message. Code word means what? Always the data word will be appended with the redundancy bit. That is code word. So here when you see, I'm adding my parity bit. So my parity bit is added, and this is my receiver side. So in the receiver side, I have a checker. You all know the generator is nothing but the algorithm we are developing, and we are adding the bit, and checker always will check whether it is come according to the logic. Okay, in that, if my code word is matched, then automatically it will accept the data. If not so, it will discard the data. This is what now simple redundancy check. That is, we used to say vertical redundancy check or simple parity checker. So what is the concept, ma? Even number of ones now, what is the parity bit? 0. Odd number of ones now, what is the parity bit? 1. Have you understand? Have you understand this logic? So can you tell me 1 0 1 1 1 1? What is the parity bit for this data, ma? What is the parity bit for this data? What is the parity bit for this data? What is the parity bit for this data? Kindly tell me what is the parity bit for this data?
Okay, I've enabled this DAG program using arrays, right? Okay. Yeah. Okay.
Yeah, tell me, I'm asking the question. For this particular number, what is my parity bit? 1, 0, 1, 1, 1, 1. What is the parity bit for this data? Yeah, odd parity. Yeah, Pujita, correct. Odd parity, don't say. I have, what is my parity bit now? 1. Sagar Kumar, have you understand? What is the parity bit I have to add now? That is 1. The parity bit value is 1. Is clear? So, yeah. Okay. So you all understand? Similarly, if my data is 1, 0, 1, 1, 1. Okay. Here, what is my parity bit? What is my parity bit? What is the parity bit for this example? Here my parity bit is 1. Yeah. 0. Correct. Pujita. Yeah, it's correct because even number of ones are there. Okay, that is performed in the vertical redundancy check. Okay. What's the problem on vertical redundancy? You just see the data has been sent here. You all know 11001. It's a even parity generator. You all know this is my generator where it will check for odd number of ones. If odd number of ones is there, I have to add my redundancy bit as a 1. So here you see 1, 2, 3. Maybe odd number of ones means 3 ones will be there, or 5 ones will be there, or 7 ones will be there, or 9 ones will be there, or 11 ones. So it may be in the count of like this. So here I'm checking in this particularly, I'm having 3 ones. So 3 ones means by checking this vertical redundancy bit, I have to add 1. So that one will be appended with the original message and it will be sent to the receiver side. And in the receiver side, what it will check now, whether my messages contains, my code word is contains even number of ones. You see 1, 2, 3, 4. Okay, it contains even number of ones. So it will accept the data. That is vertical redundancy check. Okay, so we will see one simple algorithm, world. Okay, I'm sending the 5-character word WORLD. You all know we are using the ASCII code. Okay, so in the ASCII code, the equal binary code will be developed. So we were using that. When you see this particularly for this, you tell me odd parity or even parity. Tell me the parity bit which has to be added. For W, what is the parity bit I have to add? Tell me the parity bit. Yeah. Parity bit 0. For O, tell me for WORLD. O also, yeah, very good, 0. R also 0. Okay, good. L also 0. Good. Then D is 1. Yeah, very good, very good, very good. Very good. Thank you, Sagar and Pujita. Okay, so see my parity bit for W is 0. 0 is, O is 0, R is also 0, L is also 0, D is 1. Because I'm counting my W, I'm having 6 ones. While counting my O, I'm having 6 ones. While counting my R, I'm having 4 ones. And counting my L, I have 4 ones. So I'm checking all this are in the even number of ones. But by checking D, I'm having 3 ones. I told you 3 ones, 5 ones, 7 ones are there. I have to add my even parity bit as according to my even parity checker. I have to add my parity bit as a 1. So you see this will be added 0, 0, 0, 0, 1. So the parity bit, that is nothing but the redundancy bit will be the parity bit. Okay. Now the word is in example is received by the receiver without being corrected. This is my answer. Okay, 0, 0, 0, 0, 1. Okay, I'm checking in all that particular word. I'm having only even number of ones. 6. You all see first 6 ones, second also 6 ones, third also 4 ones, fourth character also 4 ones, and fifth character also 4 ones. Okay, now I'm saying my world is corrected. My world is not corrected. My sending messages get corrected. So in that corrected, you see in the first count, I'm having how many ones, ma? How many ones are here? 7 ones are here. Here, how many ones are here? 6 ones are here. And here, how many ones are here? 5 ones are here. And here, how many ones? 4 ones. And here, how many ones? 4 ones. So while I'm seeing that, I'm employing the even parity algorithm, but I'm getting my message 76544 now. Definitely my bit will be get corrupted. Then automatically it will discard. Ma'am, parity is added to begin or end. That depends on the. Actually, here they added the parity bit at the end. But normally, when you see that some of the example, they will put the redundancy. But we all used to say up and then up and it all will be in the redundancy bit will be here. Then the data will be here. Okay, that's not a thing. But while receiving in the receiver side, we always know that the LSP will go first, then last MSP. Okay, so normally parity bit will be at the beginning. Yes, it will up and the word they will say up and. Okay, now here this message will be corrupted, so it will be. So here it will be not corrupted. Why? Because now even number of ones. Here odd number of ones. Okay. Now we can say that it will detect single burst error, but single bit error, but it cannot detect a burst error. Why? Because now, for example, I am sending 10110. Okay. And we can say according to the concept, we can say that this particular message is not correct. Why? Because now I am having 3 ones. So single bit error, it automatically, single bit error means what? Ma? One, it will detect only a single bit. One will be changed to 0, 0 will be one changed. But here I'm saying 1, 0, 1, 1, 1. Okay. And we all know that it will check. Okay, 4 ones are there. Why? Because now, if total number of 1 is odd only, it will detect correctly. If total number of 1 is in even, it won't detect, because if in my receiver side, when you see to that, I'm getting even number of ones now, automatically it won't check for all the bits. It will say that the received message is correct. It's clear. The previous exam is the best exam. Instead of 7-1, I'm sending 8-1. It will say that yes, it's correct only. It's clear. So we can say that vertical redundancy check is employed only for the single bit error. For burst error, if it is odd number of ones only, it will be valid. Even number of ones, it is not valid. That's why it is saying that. Yes, clear? Okay. Now, students, listen. The next one is LRC. Student, all of you listen, ma. LRC. LRC means what's ma? Longitudinal redundancy check. Okay. Longitudinal. Actually, when you see that vertical, it's a simple parity checker. One-dimensional we say. But LRC is always said that it's a two-dimensional checking. Okay. Once again, wait. Okay, actually, when you see to that, LRC is for two-dimensional check. Okay. So now what I'm going to do, I'm going to check this data blocks. I'm going to check this data blocks. So what I'm going to do, I'm going to place all this data in a row wise. So first my data is, you may take it this one example. Okay. 1, 1, 1, 1, 0, 0, 1, 1. First data, and this is my second data, and this is my third data, and this is my fourth data. Are you all clear? Okay. Now LRC, longitudinal redundancy check. Now you check in column wise, and you just tell me what will be the bit I have to add according to the even parity logic. How many ones are there, ma? So what is the first bit? How many ones? Check in the column wise and tell me. Tell me the LRC value. Just put it in the chat, ma. Put the LRC value in the chat. I have one simple example I will say. Here 1, 2, 3. 3 ones, odd number of ones. So odd number of ones now I have to add 1. Okay. Now you go with this example. 1, 1. Even number of ones. So it is 0. So tell me the LRC value. No. You tell me 3, 6, 8 bits. Tell me the LRC in 8-bit, ma. Soumya, Pujita, and Sagar Kumar is now responding. I think I got 3 people to respond me. Yeah, put that LRC 8-bit because who is going to put first? Yeah, tell me that LRC value. Yeah, very good, very good. Pujita, Soumya have put it correctly. Yeah, very good, very good. So you all know here 1, very good. Here 1, and here 0, and here 1, and here 0, and here 1, and here 0. Very good. So L or C, it's nothing but, yeah, longitudinal. Soumya Deep is 1 word. Okay, okay. Soumya Deep is 1 word. Yeah, Soumya Deep, according to our logic, 1 byte 8 bits, so it will be 16 bits. So Soumya Deep is 1 word. Okay, I will pronounce correctly. Okay, okay, thank you, ma'am. So 1010, 1010. It's my LRC. Have you understand? So LRC means how it will be done. Now you just see the next slide. This is my first data block, second data block, third data block, and fourth data block. I am adding this LRC that you calculated now 10101010. So this is my direction. So you have asked now how the direction of movement is there. So when you see here, my redundancy bit is appended with the original data. That is my LRC that will do longitudinal redundancy. But what is the advantage, you may think now, that single bit error only computed by the vertical redundancy check. But obviously this LRC have a method to compute the multiple bit, or it may be used to employ for the burst error. So I can do it for burst error using the longitudinal redundancy check. Okay. Yeah, now I think, oh my God. I'm just doing this correction. Yeah, find out the redundancy bit. Find out the redundancy bit for this particular data. Same data, va? You all know this is my original data. Okay, this is my data 1, data 2, data 3, data 4. So even they find out the row parties as well as column parties, but you all know the column party will be added as a LRC. So find out and tell me the answer. Yeah, Soumya Deep have calculated correctly. Yeah, here 0, 2, 1, 0, 1, 0, 1, 0, 1, 0. Very good, very good, ma. Very good, very good. I think I will remove this with the eraser. Is clear? Okay. So sometime they told you now, the row pixel also they will do this, and they along with that they will send. So we have some algorithm, only the column entry will be taken, and here you all know the row parties also take the LRC, and there I will one more bit is added in that LRC. They will send along with the data movement. So you see here, when you see in the row 2, 3, 4, 5 ones are there. So this will be my, here 5 ones are there, and here you see 1, 2, 3, 4, 5, and here 5 ones again 1, and here when you see 3, 4 ones are there. So my even parity is 0, and here when you see 1, 2, 3 ones are there, again my value will be. So again when you see that 1, 1, 0, 1, again 3 ones are there, so I will have 1. So the LRC, we have a thing, not only for that, always it will use to employee for the 7-bit. The 8th bit also will be added for the LRC, and it will be checked and it will be sent. Is clear? So you see the row parties also will be added here. 1. Okay, when you see 1, 1, 0, 1. And this is the LRC with 8-bit. So all the data is sending along with 8-bit, because row parties are added with every original data. And then we have one more column parties, that is nothing but this is my LRC. longitudinal redundant check. Ma'am, or LRC second 2D parity check different. No. First I have checked only with column parties. I told you now, this is only with column parties. I didn't employ the row parties here. But when you see here, I'm checking both row as well as column. And while I'm seeing this row parties is added with the data and it is sending. And one more data is also with the column. So you have seen this is in green color. I think you can able to see or not. Sagar, you may unmute and ask. I can't understand you without. Ma'am, so either we can check anyone or both or all permissible. That is depending on the algorithm. So here, when you see the previously, I have checked only with column entries.
Ma'am.
Yeah. Ask Sagar.
So, ma'am, is it compulsory that we either is it allowed that we can either check column or either row or both?
Yeah. Actually, we have only column checking, or else it will check both the row and column. Is clear? One is column checking method, another one is row and column both will be checked. If row and column both is checked, for every data bits, one more bit will be added from the row parties, and one more LRC will be that is as usual, that will be appended with the data moment. Okay, one is column check method. Here this is called as a column as well as row checking method. Both will be employed. Okay, that's why when you see all my data are 7, but while sending all my data having 8 bits, and LRC is also having 8 bits. But previous case, when you take this, all my data are 7 bits, and even my LRC is also, you see, not all my data are 8 bits. So LRC is also 8 bits. But when I am doing row method, one more bit will be added with original data, also with LRC bits also. Is clear? Shall I move on to the next method?
Ma'am, will the number of bits be 8 each time? Total number of bits?
Yeah, that's all depends on the algorithm. Okay, that's all depends on the algorithm. Why? Because now sometimes they will divide into block. For example, that is the next method, checksum method we apply. For example, total 20 bits is there. So in that particular algorithm, they will tell 5 blocks only allowed. So you all know 20 bits, 5 blocks now. Total number of bits is 20. And totally we have 5 blocks now, 20 by 5. So you all know how many bits in each block, ma? How many bits in each block? 4 bits. Is clear? So it's all depends upon the total number of bits. Total number of bits and dividing the number of blocks. That's why while I'm telling that the data blocks we used to say. Okay, it is a one message only, but it will be divided into packets we used to say. Now that is the way. Okay, now I will move on to the next one. Okay, I think suppose the following block is sent. Okay, hence it is burst noise. You all know that this is my 1, 2, 3, 4, and you all know this is my LRC bit. So every time I will check out with this. So when you see this here, some bits are get corrupted. Means it all you seems to be that here we see 1, 2, 3, 4, and here also you see 4, and here also when you see 3 ones are here. When you come to the here point, and here it will be correct number of ones, and here it will be correct number of, and here it will be correct number of ones. So I can say that this particular bit is corrected. So I told you this particularly LRC bit. LRC we are saying now that particular LRC will check the single error as well as it can able to check the 2 bits also. Okay, that also it can able to find out. So LRC is likelihood of detecting the burst error. Vertical, we don't have such a choice of a burst error, but LCR, sorry, not LRC. We used to say longitudinal redundancy check, and in some time longitudinal check redundancy. Both are same only. Okay, so don't get confused. LRC or LCR, they will say depending on some of the book they are employing. But normally we used to say LRC checker. Okay, longitudinal redundancy check. So it is used to check single bit error as well as burst error. Is all of you clear? Shall I move on to the third method? Shall I move on to-
Can you repeat about the restriction with LRC?
Okay, so here if 2 bits in one data are damaged and 2 bits in exactly same position in another data is damaged, the LRC checker will not detect the error. Okay, what they are saying now, do 2 bits, not only that, we are saying that 1 0 1 1 0, and they are saying consecutively they are saying that 2 bits are get corrupted. So when you see to that, here it's all depends on the bit also. So when you see here, and I take this as a 1, so here 1 0 0 0 1. Okay, so even 2 bits in exact position get corrupted, we can't able to that. LRC value will be when you go to here, I will tell you very simple example. Here my bit is 0. Okay, getting corrupted, and here it is 0. Okay, so what we used to say, it is a odd number of parity, again 1. So the 2 bits are corrupted, but my LRC won't get changed. That is 1 only. So when I'm checking also, I will get same 1. So that problem is in LRC, they are saying, because it's all not 1 bit vertical redundancy good, 2 bits, same bit, same position, it's get detected now. Then the LRC value is 1, it won't change. So because here even number of ones are there, so I have to add only 1 here. Then that LRC is correct only. But when you see to that, my data is get corrupted here, my data is get corrupted here. Yes, Sagar, have you understand that point?
Yes, ma'am.
Okay. So now, and most important method, cycle redundancy check, and it is one of the most powerful redundancy check when I'm comparing with all the vertical redundancy and longitudinal redundancy. So this we are going to see, and I told you CRC will be appended with the original data. Okay, now I think I will directly move on to that CRC method. Actually, this will be the algorithm. Okay, once I will explain it and I will come back to this method. Okay, actually here, this is the CRC, how they are generating. Find the length of the divisor. Actually, we have a data as well as we have one key. Okay, that is divisor. Divisor is my key. Okay, and you all know, if data length is L length, na, I have to add, for example, the key is 3 bits now. I have to add 2 bits because L minus 1, I have to append with the original message, and I have to do the binary division. Why I am telling binary division with the XOR truth table? Now, this is the thing. We all know that binary subtraction or binary addition, if both are 0, my answer will become 0. If both are 1, that time also my answer is 0. If my both the inputs are different, my answer will be 1. So that we are going to do. I think I will explain you with this example. Please kindly take down the notebook and write. Then only you will understand how CRC bit is generated using the binary division method, cycle redundancy check, and it's one of the important example. Okay. Now this is my message. 1 0 0 1 0 0. This is my message. Okay, divisor we used to say, or key we used to say. They will send the message along with the key, and now we are going to see how CRC is going to be developed. Okay, now how many bits in the divisor, ma? How many bits in the divisor? 4 bit. So 4 bit is in the divisor. I have to add 3. Okay, 4 we have seen now. If length of the divisor is L na, I have to add L minus 1 bits to the original message. So I am having 4 bits now. I have to add, I will add in separate color.
many students have completed the program?
0, 0, 0. Is clear? Why I am adding now? Why I am adding? Because now,
Girls are sharing
okay. Why I am adding now? Because this is my extra bit. This is my extra bit because this is 4 bits now. Then automatically this will be 3 bits. It's clear? L bits now. L minus 1 bits will be appended. Now I have to perform the binary division. Okay, now I have to perform the binary division. Okay, now we will perform the binary division. Kindly listen. First time do 1. Okay, so now you multiply 1, 1, 0, 1. We all know. Perform the extra truth table. 1, 1 means what? 0, 0. And here what? Here what is the value?
what is the status of the program? Share is
Tell me, Ma. Are you listening?
I'll come from the last.
How you started proceeding for division?
Vaishnavi share is
Cycle redundancy checker means this is the message. Are you listening, Sagar? This is the message.
Yes, ma'am.
This is the divisor. This is my key. I'm having divisor is 4 bits now. 3 bits will be appended with the original message. That's why I have written in blue color. Okay, now I have multiplied with 1. First I'm taking my divisor is 1. Okay, it's not a divisor quotient.
Is it up to 1? Is it
No,
up
no,
to us
you all
to
know
choose
if-
the question?
Yeah, quotient is 1 only. But at what condition I have to choose 0, I will tell you. Okay, now the quotient is 1 only. You have to write always quotient 1. You all know become 0, same data will come. That we know. Okay, I'm choosing my quotient is a 1. So 0, 1, again 1.
Okay,
Yes,
Shweta,
clear.
share
Okay,
is
now I have to add this one more bit here. What is that bit? 0. Is clear? Now again I have to take 1. Again, what is the value, Ma? What is the value? 1, 1, 0, 1. Okay, now again perform the 0, 1. What is the value? 1. 0, 0, 0. 0, 1, 0. Again, we all know 1 minus 1, 0. So leave it. Okay. Sorry, here it is become 1 now. Am I correct? 0, 1, 1. 0, 0, 0. 0, 1. Again 1, 1. Is correct or not? I'm committing mistake. No
Correct,
one.
ma'am.
Okay, now I have to add 1 more 0. Okay, again I have to multiply my quotient with 1. Okay, now again you do 1, 1, 0, 1. Okay, now again you perform 0, 1, 1. Same thing only I'm doing. 1, 0, again 1. 0, 1, again 1. And again what will be the value? 0. Okay, and I have to take 1 more 0 here. Okay, again I have to multiply with 1.
Sharing share
Yes.
is ma'am.
Yeah, 1, 1, 0, 1. Okay.
Sharing. So you people are just logging into the device.
1, 1. Okay. So 0, 1. What is the value?
Sharing.
1. 1, 0. What is the value? 1. Here, when you see that I'm getting only 4 bits, I'm subtracting. The leftmost bit also becomes 0. So you see, the leftmost become. So when I'm taking here, LSB, actually I'm getting 4th bit always 0. But here, 4th bit is also 0. 3rd bit is also 0. So at that circumstance, I have to add my quotient as a 0. When I have to add 0, when the leftmost, that both the remainders are become 0.
Ma'am, couldn't see the right side, ma'am.
Can you able to view this?
Share.
Right side you can't see. Which you can't see here. Actually, this is
Ma'am,
the.
the one which you draw, we can't see, but the one on the slide, we can see.
Oh, okay, okay. I think this is you got. I think you may just see this. Yeah. Okay, actually, I am performing 1, 1, 1. When at what condition I am putting 0 now? At what condition I am putting 0 now? Here you have seen my here also 0, here also 0. The 2, and you all know that the LSB becomes 0. I have to add the 0 here. Once I add 0, once again you multiply 0, 0, 0, I will get 1, 1, 0. And again I am adding 1. Again you see what is my reminder. What is my reminder, Ma? What is my reminder? I think I have to perform for 1 more. 0, 0, 1. This reminder is my cycle redundancy checker. This reminder is my cycle redundancy checker. Is clear? I think now you able to see here? Can you able to see?
Give some space.
Can you able to see, ma?
Yes, ma'am.
Yeah, now you understand. You just see well here. This is my divisor and this is my message. Why I put 3 ones zeros, ma? Because my divisor having 4 bits. I have appended with the 3 bits and I performed when I am putting 0. When my LSB bit becomes 0, then automatically I am putting 0. And you all know this is the reminder. The reminder is what? 001. You all know that is my CRC. CRC means what? Cycle redundancy checker. Is clear? Okay. Now my data is transmitted. Okay. Now what you have to understand now, whether the received data is correct or not, I have to do now. Because parity checker, very simple. We have odd number of ones, even number of ones I am doing. But here you see, this is my data. I have to check whether my reminder is, I have to check whether the data which I have received in the receiver port is correct or not. So you all know that what message I am sending? 1001. This is what, ma? This is my message. This is my data. Is clear? And 001 is my CRC. Now it is sent from the sender side. CRC is what? 001. 001 is nothing but my quotient. 001 is nothing but my quotient. Did you perform the same binary subtraction in your notebook, in your class, in your notebook, ma? Perform same. Did you perform this? Then only you will understand. You can't.
Yes, ma'am.
You perform it and come to the conclusion that you are getting the reminder is 001. Then automatically that reminder is your CRC, cycle redundancy checker. Okay. Now this is my original data. Am I correct or not? This is what, ma? This is my original data. Okay. And this is what? This 001 is what? This 001
Key
is
minus
what?
1, ma'am.
No. You
CRC,
say,
ma'am. CRC.
yeah, this is my CRC, cycle redundancy checker. Whether I have to, sender has sent, but a receiver has to know now whether this one is correct or not. So once again, receiver side also with the same divisor, it will perform the division. At that time, if I'm getting my reminder is 0 now, my data received is correct, or else my data contains the error. Have you understand how it is checking from sender?
Ma'am.
Yeah. Can anyone tell?
Ma'am, we can check that at receiver side, we will be able to check that the error has occurred with the data. But how will we define that at which position the error is?
Yeah. But in this particularly, if it is all zeros, it will accept this particular bit is correct. If it is not all zeros, if I have an error, then automatically it will discard. It won't keep the data. So you all know how it is performing now. You just see, this is my data. I think I will take one. Same data I will take. Okay. So here, I think you leave it. I'm sending this data. I'm sending this data. Now, what is the reminder for the both the cases? Both the cases, what is the reminder? What is the reminder? You have told now that it won't check. Here you see this bit is corrupted. But here while I'm saying this bit is corrupted. But what you're saying, it having the remainder of 1. And here it is having the remainder of. So automatically it will discard the data. It will discard the data. Have you understand? Have you understand how it is performing?
Yes, ma'am.
Yeah, first my data is nothing but this is my data. I think this is my data. This data is performed the division or key. We used to say divisor is my key. Okay, in sender side, it will add the data depending upon the number of bits it will perform. So finally, it will get one reminder. That is my CRC. So original message data will be data plus CRC will be sent to the receiver side. In the receiver side, once again, the same division it will employ. If So this particular slide says that no error. No error means what? My reminder is 0. If my reminder is 0, I won't get any error. Or else here I can understand my this data is get corrupted. Here I can understand my this data is corrupted. Whatever the data is corrupted, that is not a problem. I am getting the reminder. So I can clearly say that there is an error in transmission. So automatically this data will be discarded. You all know the key I'm saying now, this key is my divisor. Is clear? So for example, how many now you will understand very well. This is my how many bits ma data length? 6 bits will be there. 1 0 0 0 1 0 0. We all know that the key is having 4 bits. So 3 bits will be added 0 0 0. Then one more thing is CRC. CRC is nothing but my reminder. So you just see my data is only 6 bits now. Along another 6 bits is developed. One is for appending along with the divisor, and then the CRC bit. So that will be sent. But when you see that to perform the addition only, we are using this. But once a binary division is completed, we send only the data plus CRC only. Now you come to this PPT. Okay. Now have you understand that?
Is this key fixed or it changes with the data, ma'am?
Yeah, definitely CRC will change. I will give you one assignment. Next class, you are supposed to tell me. Actually, I will come next class. I will only come for your next class. So I will tell you, please kindly, now you understand, this is my data. Okay. Then I am doing divisor. We all know I am doing divisor. Okay. And in the divisor, I am getting my CRC. This is n bits. That CRC will be added with the data and it will be. So when you understand.
Time is about to go up, ma'am.
Oh, sorry. So you just understand only simple thing. Reminder is 0, na accept. If reminder is non-zero, na reject. That is the thing. If reminder is 0, na accept. If reminder is non-zero, na reject. Okay. You people take down this assignment problem and you tell me this particular sheet alone, take the snapshot. Okay. Find the CRC for 1100 1101. For this, you have to find out the divisor. What is this divisor? Na? X cube is 1, x square is 1, x is missing on this polynomial. So 0 and the constant is there 1. So you find out, this is your key. Will you find it and tell me in the next class? Please kindly take down the snapshot of this. Okay. Next class, you are supposed to tell me the answer for this.
Okay.
Yes? Okay.
Thank you, ma'am.
Thank you all. Thank you all.